So ammonia, ammonia, NH3, is a weak base. We're going to talk about NH3 a lot because it is such a common weak base. However, if you see something written as ammonia, you want to know that that's NH3. Let's write the equilibrium equation for hydrolysis of ammonia. And hydrolysis, so hydro is water. So hydrolysis is the reaction with water. So we're looking at NH3. Remember that acids and bases are aqueous, plus H2O, water is a liquid. Now there's two ways that we know that it's equilibrium. One, because it says, right, the equilibrium equation. But two, because it's a weak base. Weak acids and weak bases exist at equilibrium. Now we have to figure out what the products are. We know that NH3 is a weak base because it tells us in the problem. So if NH3 is the base, that means that H2O has to act as the acid and donate one proton to NH3. So we're always looking at these acid-base reactions. So when NH3 accepts the proton, it becomes NH4+. So that's the ammonium polyatomic ion. And then when H2O loses its proton, when it donates the proton, it becomes OH-. Ions are always aqueous. So that's our reaction for number one, the hydrolysis of ammonia. The reaction of NH3 with H2O is at equilibrium with NH4+ and OH-. Then number two, if more ammonia is added to the equilibrium, what will happen and why? And I said think about Q versus K. So if we add more ammonia, I'm increasing the amount of NH3. So this reaction was already at equilibrium. Then we said, okay, we're going to add more NH3. Now we're disrupting equilibrium. So now we're disrupting equilibrium. And remember when we talked about disrupting equilibrium, that's looking at Le Chatelier's principle and Q versus K. If I think about Q, just like K, just like an equilibrium constant, Q is products over reactants. So the concentration of NH4+ times the concentration of OH- over the concentration of NH3. Water is not there because it's a liquid. So this is Q. The reason that this is Q is because, remember, there's only one thing that changes K, temperature. That's why Kw changed at different temperatures, because it's an equilibrium constant. But if we're just adding something, we're increasing the concentration, think about it as increasing NH3. So we're increasing the amount that's in the denominator when we're looking at Q. Up here, if it's at equilibrium, Q equals K. However, we've made a change. We've added more to the denominator. If you are dividing by a larger number, you're making Q smaller. So when we add to the denominator, Q is now less than K. And if we think about equilibrium and what it means if Q is less than K, to get back to equilibrium, Q has to get back to K. Equilibrium is only when Q equals K, and so to get back to equilibrium, Q needs to increase. And for Q to increase, we need more products, less reactants. That's what this arrow represents. This arrow represents which way the reaction is going to proceed. The arrow points to the right. That means that the forward reaction is what is happening. Reactants are going to form products. So we'll say forward reaction will proceed to create more products. So again, the forward reaction, so our answer for number two is that the forward reaction will proceed to create more products. And the why is because Q is less than K. So to get Q back equal to K, we need more products. We need to increase what's in the numerator And that means we'll use up the reactants in the denominator to get Q back equal to K. So this is actually going to help us with the demo that we do a little bit later, but also just bringing back the idea that equilibrium is still here. Right, we're still doing acid-base equilibrium. So first thing is just looking at the rest of the week. So we're going to start Unit 8. Unit 8 is Chapter 17. We're actually splitting Chapter 17 in half. So 8.1 to 8.3 is more with acids and bases. So we'll spend the next 2 weeks or so still talking about acids and bases, looking at titrations, so what happens when we add an acid to a base, looking at buffer solutions, which we'll talk more about hopefully Friday. And then next week, right, we'll continue on with, that's when we get to titrations, is next week. Mastering is actually already open, so it's 25 questions. There are 23 that are credit, right, so 23 points, and then there's 2 extra credit as well. That's due Wednesday the 3rd. So I was trying to look at when we would probably be done with the first part of Unit 8, because I'm completely splitting it in half. So we'll have like separate tests and quizzes for the first part, separate tests and quizzes for the second part. So we should be done with acids and bases around the 3rd. So that's when mastering will be due. If we have to push it back a couple days, we'll push it back a couple days, but it will not be due before that. So March 3rd will be when that is due. Like always, I have everything split up by video. So you'll see that mastering is just 3 videos because I'm splitting Chapter 17 in half. Now, kind of going along with extra credit, because people were like, mastering only has 2 extra credit. Yes, but we do this optional bonus every year. If you want to do it, you could do it. If you're like, I don't want the bonus, okay, fine. You don't have to. But what we do is we do this optional bonus that goes along with the food drive. So this is what that half sheet was. It was over on the side. I will tell you that I'm going to create some like tutorial videos to help you with the process of solving all of the different thermochem problems. So again, this is optional. It's up to 10 points. You can just do part of it and get some of the points, or you can do the whole thing and get up to 10. So the first thing, because this revolves around the food drive, is you can bring up to 10 items. All right, so cans, boxes. I just kind of gave what the nurse does not want. But 10 items, right? Whatever items you pick. With these 10 items, right? Because I'm not just going to say bring in 10 items and give you bonus, because of course I'm not. So you have to do some things with those items. So for the first one, for each food item, so you bring in mac and cheese, chicken noodle soup, tomato soup, I don't know, green beans. For each one of those items, you need to do a quick conversion. Convert calories. So notice the capital C, that's a food calorie, which is a kilocalorie. Convert that to joules for 1 serving. I even gave you the conversions here. So if something is 100 calories, that's a capital C. That's a kilocalorie. So 1 food calorie is 1,000 calories, which is 4.184 joules. If you have a can that has 0 calories, I still want you to show the work. Start with 0. Yes, your answer is 0, but the whole point is to do the conversions. And then the second thing, so this first part, people are like, okay, that's fine. And then it gets to down here, and they're like, really, MC delta T again? So for 1 food item, pick 1. Box of mac and cheese. You're going to do 3 different things. So the first thing is, it says if using a 100-gram sample of food, determine what mass of water could be heated by 5 degrees Celsius. So Q equals MC delta T. Q is coming from the food. M is what you're solving for with mass of water. C is the specific heat of water. Delta T is 5 degrees. All right, so that's an MC delta T. The second one is actually a heating curve. All right, determine the mass of water that could be heated from -5 to 5 degrees Celsius. So you have a heating curve that actually looks like this, -5 to 0, up to 5. So when we talked about this, Q1, Q2, Q3. So the second one is a heating curve. Again, I'm going to make like a short playlist of videos, one for each, just to give you hints, right, direction as to which way to go. And then the third one, if you ate 1 serving size of food, how many grams of fat could be metabolized? So that's a thermochemical equation. It says that fat is being combusted, so here's your fat, here's your hydrocarbon, plus O2, yields CO2 plus H2O. So this third one is actually a stoichiometry with delta H. So looking at 1 serving size of food, right, whatever that energy is, whatever that in joules is, joules to kilojoules, kilojoules to moles, right, moles to moles of fat, moles to grams. So it's been a while since we've done thermochem. The plan, I probably won't get to it tonight, maybe tomorrow, I'll make these short tutorial videos. Even if I just take my phone and I set it up above and work through it for you. I'm going to find random things in my pantry to make these videos with. But I'll do one for each. So like I'll do, here's a conversion, I'll do one for this, so there'll be 4 videos. So you can click on whichever one, I'll put it on Classroom. That way, right, if you need help going through, you can pick your own food.
So like get the whole 10 points, would it be like you bring in the 10 cans and do all the conversion?
Yes.
Okay.
Yeah. Yeah,
Is this
so...
master? I mean, sorry, Classroom. I don't know why I said master. I meant Classroom.
Wait, say what?
Is this on Classroom? Like the sheet?
I just put it in the chat. So it says, there you go, bonus project info sheet. And I have, if you want like a hard copy of it, you can grab one tomorrow too. I had it for you guys yesterday, but you know. So yeah, I'll do kind of short tutorial videos for this, but yeah, it's, if you bring in 10 items, you do all of these, you'll get the 10 points. Now, here's the thing. Thing 1, it just so happened that it's due the same day as mastering. I didn't mean for that to happen. Food drive is done the 5th. We have to give the nurse and like the nurse's aides plenty of time to come get all the cans. Usually the entire front of the room is filled with cans. So it's due the 3rd. Plan accordingly. I have no idea what day the 3rd is. If it's green or gold, I don't know. But you don't have to wait until then to turn it in. As soon as you turn it in, I will put it in Power School. So if you turn it in on Monday, the 10 points will go in Power School. But when you bring the cans in, because this has happened many times and we didn't realize, a lot of times people will bring the cans in the morning, and if I'm in a meeting or who knows where, people will set their cans up here, which is fine, but their piece of paper that has all of their work on it is also in that bag. And I don't know. And then the nurse's aides will just randomly start coming in and collecting the cans. And then I don't see your piece of paper. So, if you turn cans in, so you come in the morning and you don't see me in here, you can set your cans up along the front of the room, but make sure that your piece of paper with all of your work, just set it on my desk. All right, I'll see it on my desk. I'll put it into a pile. You'll be good. So whenever you want to turn it in is up to you, but just plan accordingly because it's due by the 3rd. So I'll keep like notices up on the board. I'll keep reminding everybody, but the 3rd is when this is due. So you can even get partial. You bring in 5 cans and you do some of the conversions. Right? You can get 5 points, so on, but up to 10. Or you can not do it at all. Fine. So that's it for the bonus. I just wanted to make sure to talk a little bit about it. I will be making these videos, and I'll add this into Classroom with those videos as well. So what I'm going to give you guys time to do is watch the first video in Edpuzzle. So it's already up in Classroom. It's 9 minutes. Right? It's not long, but because we didn't have the notes yesterday And, yesterday was just its own thing. I'm going to give you guys time to watch it today. So I have 2 empty beakers, and I'm going to add distilled water to each one. So this is just water right out of the distilled water jug that's still on the back lab table. And I'm going to try to add about the same amount of water. So really I'm just creating a solution. And actually what I'm doing is I'm creating an ammonia solution. So I'm adding NH3 to both of these. So right now all I'm doing is I'm adding NH3 to each of the beakers. Right, still didn't do anything. An ammonia solution is clear. So right now I have 2 NH3 solutions. So on the board, let's go ahead and rewrite what we wrote in the do now of the equilibrium that exists when ammonia is added to water. So remember in the do now we said that NH3 is ammonia, that's a weak base. NH3 is a very common weak base. You need to know that ammonia is NH3. We add it to H2O, which is a liquid. And because NH3 is a weak base, it exists at equilibrium. Remember that weak acids and weak bases exist at equilibrium. Because ammonia is a weak base, water is going to act as the acid. And so water is going to donate its proton, just one of them, to NH3. When ammonia, NH3, accepts a proton, accepts an H+, it becomes the ammonium polyatomic ion. Ions are always aqueous. And when water donates its proton, it becomes OH-. The production of OH- is why we classify NH3 as a base. And so what I'm actually going to do is I'm going to add phenolphthalein to each of these. We briefly talked about phenolphthalein in the last unit. It's an indicator that turns pink in the presence of a base. More specifically, it turns pink when the pH is somewhere between 8 and 10. And so, try to add the same amount of phenolphthalein to each beaker. All right, I can swirl them. All right, you notice that it turns pink. Use my stirring rod and mix them. So phenolphthalein is not part of this reaction. Phenolphthalein is just something, it's an indicator that turns color, and phenolphthalein turns pink in the presence of a base, pH 8 to 10. So these are both the same thing right now. These are both NH3. Now I'm going to look at what happens when I add ammonium chloride. So in this beaker, I have solid ammonium chloride. So I'm going to add some of this ammonium chloride just to one of the beakers. Probably too much, but that's fine. So I just added solid ammonium chloride to this beaker, and it turns clear. So remember that phenolphthalein turns that pink color when the pH is between 8 and 10. Well, it's no longer pink, so something happened. And so what we're going to do is we're going to actually look at what happened to this equilibrium for it to shift in a way that it went from this fuchsia pink color back to clear. So we said that we were adding ammonium chloride. Ammonium chloride is NH4CO. Now, before we've been talking about acids, bases, and salts. So what's going to become important is that we can label one of 3 things. We can label an acid, we can label a base, and we can label a salt. Acids are a little bit easier for us to tell because they start with H's. Most bases end in hydroxide, but not all of them, right? We've seen that NH3 doesn't end in hydroxide. A salt, though. A salt is an ionic substance. It needs a metal and a nonmetal, or it needs polyatomic ions. A salt is a cation and an anion together. NH4Cl, this is ammonium, which is a positive polyatomic ion, and chloride. This is a salt. Remember potassium, nitrate, ammonium, and sodium? Right. Anything with potassium, K+, nitrate, NO3-, ammonium, NH4+, and sodium, Na+, is always soluble. So if it's always soluble, that means it's a strong electrolyte. It completely breaks apart. So ammonium chloride, when you put it in water, actually breaks apart into NH4+ and Cl-. So when I'm adding ammonium chloride to this beaker that was at equilibrium, I don't see chloride in here anywhere. Chloride is actually a spectator ion. However, I do see ammonium here. I see NH4+. And so what I'm actually doing to this equilibrium, what was once pink, this is the equilibrium of NH3 with H2O. It turned pink only because we added the phenolphthalein. When we added NH4+, it shifted in a way that turned it clear. So we added NH4+. It was at equilibrium. We disrupted the equilibrium by adding NH4+ from the salt. So the reaction has to shift. The reaction has to shift in a way that's going to undo this change that we did. That's what Le Chatelier's principle says. So right now I have too much NH4+. So to get back to equilibrium, the reverse reaction will proceed. So I'm writing reverse reaction proceeds to use up excess NH4+. Now here's what I want to think about with that. When the reverse reaction proceeds, right, we're using up NH4+. But we're also using up OH-. Because if the reverse reaction is proceeding, that means NH4+ and OH- are reacting to produce NH3 and H2O. So as we're using up the NH4+, we're also using up the OH-. So let's think about OH-. We're using up OH-. OH- tells us that something is a base. So we're using up the OH-. So the solution is becoming less basic. And I know it's weird to think about that, but since we're using up the OH-, we're using up what makes that a base. We're using up what makes this a basic solution. So as we're using up the OH-, as the reaction is proceeding the other way, it's becoming less basic. Well, that means it's technically becoming more acidic. So the pH will actually decrease. So because it's becoming less basic, a higher pH represents a basic solution. It's becoming less basic, less OH-, because we're using it up, less OH- means it's less basic, so pH is actually going to go down. So if I actually got a pH meter in the back, I would find that the pH of this is somewhere below 8. And the reason that the pH went down is because we used up OH- as the reaction shifted the other way. And so the pH got lower. Did it get below 7? We'd have to figure out what the pH was with the pH meter. But that's looking at the conceptual idea of the common ion effect. That as you add a common ion, equilibrium will shift. It's going to shift one way or another. Does it always shift back? Probably. But tomorrow we'll also look at how pH can be affected. So we'll look at examples tomorrow with how pH can be affected as well.